Okay, so let's start with the afternoon session. So the first session is in the afternoon. I have the pleasure of sharing this. So my name is Hervé Debar from Telecom Sud Paris. And again, I would like to thank first the hosts, Maria and her crowd, for organizing this. It's a lot of work. Then the program guys, headed by Juan, who have done a great job, I think, in organizing this. This session is a little bit, I think, a change from the previous ones. We're going to look at things that are more down to earth. You know, we've heard a lot about artificial intelligence, but we actually have things underneath that make these run. And so we'll have a session that mixes various aspects of either very concrete or very abstract things. And we'll start with the very concrete, meaning the hardware layer that powers computers, with two presentations. The first one by Rafael Gomà from the Barcelona Supercomputing Centre will be on RISC-V-based chip design in the European Union. So, Rafael, you have the floor. ¿Cómo funciona esto?
Correct. Yeah. Okay, then let's talk about microprocessors, these small things that actually spend this energy that we have been talking about in the previous session. And what is the relevance of the microprocessors strategy in Europe? I'm going to skip this. Then I'm going to talk about RISC-V. RISC-V is a standard. Sometimes some people compare RISC-V to Linux. Linux in software as open source, RISC-V in hardware or in processors as open source. It's not exactly the same because Linux is something that you can download and use. RISC-V is a standard. It's a standard. You can design a microprocessor based on that standard, but by itself is not something that is a thing you can use. Although there are universities and entities that have RISC-V designs that are open source. Then open source means you don't need to pay for using it. It's modular, and you can get pieces of it depending on the application you want to do, and it's driven by a community. In fact, there is a RISC-V International. There is an entity that kind of drives and manages the evolution of this. It's not a commercial evolution. It's a community of different entities. Then what is RISC-V is a standard of what we call instruction set architecture. This means like the language that means that it's the language that hardware understands. It's the last level of software tools language with hardware, and this language. There are several definitions in the world of this type of languages, and for most of them, for use it, you need to pay. And there are, the Intel, that's PCs, that's data centers, and the ARM. The ARM, maybe you don't know, but if you have a phone, you have an ARM processor. An ARM is not an ARM processor, is a processor that is designed under the specifications of ARM. If you don't have maybe Xiaomi, but if you have any other, Apple, whatever phone you have this. This ARM is a company that was European company, from Cambridge, that was then bought by SoftBank. Then this is the world. As I said, there are other proprietary things. NVIDIA of course, is very relevant, doesn't publish directly the language of the hardware. No, you need to use the software to use NVIDIA. You use the software, the CUDA that they provide. Okay, then RISC-V, it's emerging. It has a lot of potential. It's growing very fast in all the markets because the cost and because other things like it's this flexibility and this capability of targeting different type of applications. And what is that important for Europe? No, it's important because Europe now doesn't design high level chips, no high standard chips. They rely on US designs. The Intel, the NVIDIA. Europe doesn't have this capacity of design, and this means that whatever conditions are set on Europe, like export limitations, like maybe potential backdoors that we don't know, you cannot audit because you are not proprietary of the design. Then it's one main reason is having this sovereignty on semiconductors. No, this is one reason very important in this time. It's every day more important to have this independency. Of course, this is on design. On manufacturing, we all know that for the moment we depend all on Taiwan TSMC, but before the manufacturing, we need also the design. And then there is the other reason is with this chip we can target specific applications on sectors that Europe is more relevant. No, from automotive, from energy, of course AI. The NVIDIA chips are becoming kind of uranium in the sense that you need to have it. Then is what is Europe doing in this sense of trying to achieve this independence, this sovereignty on chip design? Of course, there are multiple calls from these European entities, the chips GU, the Euro HPC for high performance computing. They are putting a lot of calls, millions on making partners in Europe, actors in Europe to design chips. Then there is this European Chips Act that is not specifically for RISC-V, but is about sovereignty, and of course RISC-V plays an important role. There are also some more commercial joint ventures like Kintauris with several important companies, and also, for example, one critical application like space, the European Space Agency is developing a RISC-V processor to use in their applications. Then Europe is doing several things. No, this is the previous one. I'm sorry, I'm going backwards. And of course, there are challenges for this getting established in Europe. The ecosystem is not at the same level as ARM, because you don't need only of course the processor, you need the tools, you need all the utilities, and this is being done, but it's not at the same level that big companies have already done. No, specifically all the tools to design chips, in fact, are American-based. No, Synopsys, well, Siemens, but Siemens is an acquisition of an American company, and the other is Cadence, that it's also. Then this is a very important point that we need to develop jointly with the processors. There is not a killer application that says today this is the application. It's a proven business model with RISC-V in this application that it's already not at this point. And of course, as always, for startups, It's not the same to have a startup in Europe, the capital they can access, that in US. No, then there are challenges, but still there are things that are working. No, there is already some industry adoption that's going there, and that's building real products with RISC-V. And also in terms of investigation, there are several. The leadership is in Europe, although the RISC-V was, let's say, invented in US, in Berkeley. Europe has several centers of excellence. The BSc, of course, the ETH on Zurich. These are just few examples, but at least the leadership on investigation is for the moment in Europe. China is progressing a lot, then maybe will chase us. But you can see here a map of all the, not all, but a sample of all the many companies in Europe and many institutions, non-profit organizations that are already established in Europe and developing things on RISC-V. Some examples of successful companies doing real products with RISC-V processors is a sample that covers kind of different things, no? High performance computing, general purpose computing, application, mission critical applications, automotive, and cloud for and data centers. No, then there are more, but just to show that there is a set of companies that are working and successfully reaching the market with this standard. What is missing, or at least is more an opinion? No, there is not a centralized governance. No, there is a lot of initiatives on European wide, but there are also initiatives on country by country, and this is not coordinated. No, and one thing that is missing probably it's there is not this kind of project that unifies kind of the vision that, like, let's do a NVIDIA for say something, no? NVIDIA kind of European version, no? There is not. There are several projects that are very useful, but it's not like this moonshot thinking. No, Europe has done some things in the past, no, like Airbus, like Galileo, and something that is missing. As I said, the software, the design tools, something that probably we have put enough focus, and then the money at the end is we need to put the money specifically on these segments where Europe is stronger, no, and is also missing, and things like, for example, if you there is a mandate from the European Union to have RISC-V in military or in space, or if there are some kind of procurement mandates, this will also drive I don't know how much that is possible, and we know that, no, in Europe there are many different interests, but this also will help. Then this is I don't know, on overall RISC-V. I'm going to give a couple of slides on the BSc. What is doing BSc? You know, it's where there is one of the 5, I think. It's the Mare Nostrum supercomputer. It's the 8th in the world and the 3rd in Europe. In Europe, there is now not just a competition; it's a rotation every year. One of the big supercomputers is renewed with European funds. Then I'm going to skip there. In BSc, there are 250 people dedicated to the design of RISC-V, and we are participating in almost all the projects. It's interesting. You can see here these all the projects that this Euro GU and Euro HPC GU are not all of them, but most of them, and BSc is participating almost in all of them. In most of them, there are leading. These are the vintage of CPUs RISC-V that BSc is doing. Not going to do, is doing building. The vision is trying to make possible to have a supercomputer in Europe built on RISC-V. No? Today it's built on Intel and NVIDIA. We plan to have at least a rack of the supercomputer with RISC-V processors, and this is the last project, the biggest project that includes many countries and many organizations. That it's about RISC-V, that it's building real chips with chiplets with 3 branches in vector processor. That's kind of the classical supercomputing, doing mathematical engineering computation, the AI, doing AI, and general purpose processing. No? And I don't know how much time is left. Okay, but then it's, in fact, this is all I wanted to say, and it's how important is RISC-V for your strategy. Thank you very much.
I propose to keep the questions in the end, so that we have a complete session of questions. So the next speaker is Calina Ciuhu from TU Eindhoven. Sorry if I misspell your name. I tried to do my best on navigating complexity in high precision semiconductor systems. So we'll stay in a similar area, hopefully. Please.
Okay. Yes, good afternoon. And first of all, I would like to express my deepest gratitude and compliments to the organization for the opportunity to present my vision in this wonderful setting. I am Calina Ciuhu. My background is theoretical physics. I have 20 years of experience in research in industry in Philips. And currently, I'm assistant professor in electromechanics in the Eindhoven University of Technology. Yes, so today I'm here to discuss about complexity, accuracy, and information flow in high precision semiconducting system. I will start with some simple examples from the real time to dive a little bit into the concept of complexity. So some simple examples like weather forecasting or navigating through the traffic in cities like Brussels, they are all about, or they all rely on prediction models. And to come to some prediction, it's basically an integration of a flow of data, which is coming from sensors, from satellites, from traffic data, and it's integrated into this information flow in order to enable prediction. Complexity arises from the fact that these information sources are interconnecting with each other in a very non-linear way, and basically to any changes in some of them can have large consequences on the output. But also together with complexity, there is also a matter of which introduces uncertainties. And in fact, we know that weather forecasting and traffic time prediction aren't always exact. And in fact, they are always associated with ranges or probabilities. So the key message of my presentation today is that as we grow in complexity and we want to ensure accuracy in more and more sophisticated systems, we need to have an improved information flow by gathering quality data, relevant data, and also building more informative levels. So it's all based on the theme of the information. And it's exactly this challenge that is also where the high-tech industry in semiconducting is currently facing. We are witnessing an increasing demand of what we call computation density. So the tremendous advances in the artificial intelligence wouldn't be imaginable without a drastic evolution in the computational densities, which is the amount of computation power per chip size. And behind this exponential growth of computational density is the Moore's law, which over the past 50 years we've been experiencing. It's about the doubling of the computation power every second year. And AI and modern machine learning technologies rely heavily on the ability to perform a vast number of calculations and complex calculations. Mathematical operations, matrix multiplications, gradient operations, convolutions, these are some of them. Together with it, we need to have capability to cope with growing models. The number of parameters that the ChatGPT-4 is expanding to billions, if not trillions, which is again also operate with vast amount of data. Next to that, there is also demand for specialized hardware for enabling tasks of artificial intelligence, GPUs or FPGAs or ASICs that actually make these processes more efficient. So altogether, this enabling of AI requires also a lot from the computational density. And these chips that we are making, they are actually the brains of our smartphones, of our processors, of our intelligent autonomous systems. And behind this, the semiconductor industry is the engine that drives this full evolution of digitalization in all the fields. So it's fundamentally necessary to look into this. Computational density, so this is my next statement. The computational density requires high precision in this industry. And it's not only because we want to reduce the size, but it's also because so smaller transistors, but also because we need to be more accurate, for example, in designing the connectors of the electronics. You need to have extremely precise lithography in the range of nanometers of precision. Also, what was also very often in this previous session, AI is a power hunger, and it needs to be fed with electronics that prevent power dissipation. But this is not only, so this is from the perspective of performance, but concomitant with the requirements from performance, we also have to face different challenges, which are again interconnected. Basically, demand for energy efficient solutions. The critical need to reduce plastic in all these manufacturing processes and equipment. This means that we are going to look for replacements for new materials, and these materials may introduce other complexities, maybe non-linearities, as in the example that I'm going to dive into. There is also demand for increased equipment lifetime. This also, next to it, cost reduction, higher throughput, and also an envisioned reduced workforce in the future, which means that we need to think about automation of processes. Performance challenges, I would say, from society or from the evolution, this put together reflects the increase, it underscores the urgent need for an innovative approach that can ensure high performance and sustainability of this semiconductor industry. I would like to explain a little bit about the lithography process. In the lithography system, so they are at the base of the semiconductor industry, the wafer stage is actually maneuvered by roughly into steps. Is one long stroke stage, which is actually in the range of microns, and superposed with a more precise short wafer stage, which is in the range of nanometers. To realize this, conventionally, till now there have been, and still in many of these devices, we use electromagnetic actuators. But these electromechanical or electromagnetic actuators, they face EMI, so interference with other subsystems of these lithography systems, which pose a lot of problems because you need to create shielding, you need to introduce other complexities and boundaries in the system. So the technologists are actually looking at alternative solutions, and one of the solutions is piezoelectric actuators. So what are piezoelectric materials? They are materials, it's a class of smart materials. They change size under an applied voltage, electrical voltage. So they clearly they have an advantage. They do not present interference. However, they have, physically speaking, they suffer from hysteresis, which is a kind of a memory effect, and the electric relaxation, which is also a delay in the response to the electric field. So these are, again, non-linearities. So it poses a problem of complexity, and it's here where within this complex landscape, the principle of information flow and Bayesian interference become particularly relevant, as it is very important to have a good prediction, a very accurate prediction of the systems for precise control. And just like in many other real-world problems, which involve dealing with complexity, it's making prediction with uncertainty. This powerful approach seems to work for the semiconductor industry as well. So what is Bayesian inference? In simple terms, is a methodology that allows to update our predictions, sometimes called beliefs, with the use of evidence. And evidence is coming from data. And while doing this, also quantifying the uncertainty. So these three things all together. It's also interesting to mention that there are two types of uncertainties. There is an aleatoric uncertainty, which comes from random processes like noise. And there is an epistemic uncertainty, which comes from absence of knowledge. And it's exactly about this epistemic uncertainty, which is reducible, where I would like to explain the piezoelectric use case. So we can reduce epistemic uncertainty by using a physics-based model for the piezo actuators. And I will illustrate how we can do that. So it is important to have a physics-based model because we can, because these models go beyond linear approximations. And in order to understand the behavior of this piezo, we need to have a good descriptors at the interplay of several physical domains, which is electrical, mechanical, and thermal. So this gives rise to a complex, it explains the complex behavior of the actuators. In addition to that, physical models that we are developing can address nonlinearities, which I mentioned before, hysteresis and and dielectric relaxation. And another very interesting and important thing is because it offers a way to express a model in a mathematical or relationship in a mathematical way. So it enables the formalists to introduce priors into the Bayesian inference. So it can combine two methodology, knowledge and Bayesian inference, which enables us to make predictions with quantification of uncertainties. In this way, the physics-based model improves information flow because it starts with integrating information from measurements and refine our understanding. It embeds the physics in the inference process, and it provides a richer description of the system, not only because it makes an estimate of the state, but also about the uncertainty level in the state. So in essence, by combining physics-based models with Bayesian inference, we've been creating a powerful approach to address complexity and uncertainty in semiconductor applications, which lead to a better control and a better performance in the manufacturing equipment. Thank you very much for your attention.
The next talk is Laima. I'm sorry, I'm going to have difficulties pronouncing your name. Jančiūtė, something like that. Okay. On moving to a very different topic, post-quantum cryptography, which I guess you've heard of. So the floor is yours.
Good afternoon. Thanks for having me here. It's a pleasure to be here. So I'm Laima Jančiūtė. I'm a postdoctoral researcher at the University of Amsterdam. I work for the project Quantum Impact on Societal Security. And part of this research that I will be presenting today was done also together with my colleagues Otto van Dalen and Joris van Hopperken from Institute for Information Law at the University of Amsterdam. So I'll be speaking about the governance of the post-quantum cryptography transition in the EU. So to set the scene, we need to say that security of digital networks is largely underpinned by encryption. But conventional encryption is now being threatened by the fast development of quantum computing. And it is so that one day quantum computers might be powerful enough to break the currently used encryption, especially that applies to public key encryption. The main method in shielding from quantum-enabled attacks is thought to be post-quantum cryptography, which is a software-based solution, doesn't require deployment of any specific hardware, and is compatible with almost all currently used digital infrastructure. So, although it is not known when so-called cryptographically relevant quantum computers will be available, and whether they will be ever available. However, most sources mention 10 to 15 years' time when such computers, quantum computers that would be powerful enough to break encryption will be around. But why it is quite urgent to initiate transition to post-quantum cryptography, which I'll refer to as PQC, is because of the so-called store now, decrypt later attacks, whereby data can be captured now, stored, and retrospectively decrypted later when these quantum computers will be available. And because migration periods take quite a long time, and as the UK National Cybersecurity Centre has recently stated, migration to PQC is unavoidable. So various countries started acting upon it little by little. And these processes have been particularly prominent in the United States, and they are often referred to where we can say that a top-down approach in the governance of this transition has been adopted. And several years ago, various memoranda were adopted, and also in 2022, the so-called Quantum Computing Cybersecurity Preparedness Act was adopted, mandating federal agencies to initiate transition to PQC and to complete this process by 2035. And in 2023, National Cybersecurity strategy was published, which stated that private sector should follow the government model in preparing their networks and applications for post-quantum future. So various agencies such as National Institute for Standards and Technology, National Security Agency, and Cybersecurity and Infrastructure Security Agency have been releasing various resources and guidance. And most importantly, National Institute for Standards and Technology, which has had traditionally has had a global role in setting encryption standards, has now been in the process of standardization of PQC algorithms. And the first 3 algorithms were standardized in August 2024, and others are on the way. And I'm quite excited that today here I have met an author of one of the algorithms that has been recently selected by NIST for standardization and will be standardized by 2027. So although this is a US institution, but as I have mentioned, it has had a global role, and the contribution of European researchers was substantial in these processes. So in the EU, the process has been unfolding quite differently. So first of all, I would like to mention some legislation which I will argue is relevant for the adoption of PQC. In that those laws contains implicit requirements to migrate to PQC, in that they require to implement appropriate technical and organizational measures to ensure the level of security appropriate to the risks, taking into account the state of the art. And many of these pieces of legislation also specifically refer to encryption as security measures. So they include the General Data Protection Regulation, the so-called e-privacy directive, the updated Network and Information Security directive known as NIS2, European Electronic Communications Code, Digital Operational Resilience Act, known as DORA, European Electronic Identity Regulation, known as EIDAS, an updated one, and also the newly adopted Cyber Resilience Act. And many of these laws, they also enshrine security and/or privacy by design principles. So these are also relevant for encryption and transition to PQC. So at the national level, the process has started several years ago at the national level with various national initiatives and various national institutions. In particular, cybersecurity authorities have started publishing various resources, recommendations, and guidelines in countries such as Germany, France, the Netherlands, Spain, Czechia, and Italy. And some of these countries have been quite active in initiating this process. Now, at the EU level, although the EU has long been funding the research into PQC, and in particular in 2024 and this year, the funding of projects for deployment of PQC and transition to PQC has intensified, but a more concrete policy has been articulated at the EU level only last year, and most notably in April last year, the European Commission issued a recommendation on coordinated implementation roadmap for transition to PQC, calling on the member states to create within 2 years to create a roadmap based on which then countries would develop their national plans for transition, and so that the process of transitioning would be synchronized across the EU, and also to select the algorithms that would become European standard. And the Commission also said that if the member states don't act upon it, then it might consider also binding measures, proposing binding measures, but binding measures are not necessarily a silver bullet, because as one of the previous speakers has also already mentioned today, for instance, the NIS2 directive has been really badly transposed by the member states. So nevertheless, the member states have started actively working on it, and a work stream on PQC has been created within the NIS directives cooperation group, which is co-chaired by France, Germany, and the Netherlands, which have been the most proactive member states in promoting the transition to PQC. And the first output of this group was a joint statement issued in November 2024, calling on organizations and companies to make transition to PQC a top priority. And currently this group consists of 24 member states. And the next output, a concept paper, is expected in spring-summer 2025. So regarding other policy developments related to this transition, we can mention the Commission white paper entitled How to Master Europe's Digital Infrastructure Needs in February, which was released in February 2024. And apart from highlighting the importance of transitioning to PQC, it also mentioned that quantum resistant cryptography is also intended as part of security measures in Cyber Resilience Act, which is quite important because, like I mentioned before, these various pieces of legislation, they don't specifically refer to PQC because they are also have been drafted based on the principle of technological neutrality. So these specific references are quite important. And also in June 2024, several EU agencies involved in the area of law enforcement and justice issued a report on encryption, where also the importance of adoption of PQC to secure systems has been highlighted. Then another reference to so-called quantum threats is contained in the delegated regulation specifying the implementation of DORA in the recital 9, which states that financial entities in assessing their suitability of their cryptographic measures should take into account the latest developments, technological developments, including quantum advancements. And the latest document, there's an error on my slide, it should be April 2025, when the so-called Protect EU, EU internal security strategy has been adopted, which also highlights that it is crucial to deploy PQC for security of sensitive communications, and that the high-risk use cases should become fully quantum safe by the end of 2030. Now, this PQC transition is embedded in quite an interesting institutional context, because security and defense policy in the EU is predominantly a member state competence, but and encryption and cybersecurity is traditionally has been attributed to this area. But already in 1997, the European Commission, in its communication called towards European framework on digital signatures and encryption, has stated that encryption has been increasingly integrated into commercial systems and applications. So, and its importance for the development of the so-called information society and the functioning of internal markets. So we cannot say that it is an entirely defense area. And as we know now, the EU has already quite vast cybersecurity acquis and policies, which also makes references to encryption. So I also would like to mention the contributions of some EU-level actors to this process. So, for instance, the European Parliament in 2021 in its resolution in response of the European cybersecurity strategy highlighted the importance of research into PQC so that it becomes a cybersecurity standard. And in March 2024, a group of MEPs wrote a letter to the EU institutions such as European Commission, European Cybersecurity Agency, ENISA, and European Data Protection Supervisor and the European Data Protection Board, urging them to start promoting the transition to PQC. And in November 2024, the European Parliament published a briefing on quantum safe cryptography. Then the European Cybersecurity Agency has published a couple of reports advising on the migration to PQC. The Europol has established a so-called Quantum Safe Financial Forum a year ago, which at the beginning of this year has issued a call to action. And Europol has also published in 2023 a report on quantum revolution, which also highlights the importance to migrate to PQC. And also the European Cybersecurity Competence Centre is involved in the management of various grants and projects that are directed to the deployment and transition to the deployment of PQC and transition to PQC. Just to conclude, the transition to PQC in the EU is quite a complex process. It involves various actors at various levels, and it involves various contexts, such as various competences and various legislation. So that is all from me. Thank you very much.
Thank you very much. And so we will go to the last talk. So Professor Ivanka Popović from the University of Belgrade will approach even before processors. We'll see what metals are about.
Special thanks to the organizers of this meeting for recognizing the relevance of the topic I shall present, and therefore thanks also for the possibility for me to present it. In the previous session, we were talking about impacts of manufacturing, and I think this could be quite useful as a reference, because of course the green transition involves many aspects, and I will only deal with a very small part of that. But I think what's very important to talk about is that the green transition can only be successful if it's done in a sustainable way, and also that there is a holistic approach that will look into all aspects of what the green transition will bring. And I will use the example of Serbia, because the question is whether this green transition can be equally implemented in all areas, in all countries, because, for example, I will implement or show you the case of a country where there is very weak rule of law, and therefore we are in need of regulations that maybe are above the national level. So just very briefly, I will talk about the mining tradition. I'm not a metallurgical engineer, I'm a chemical engineer, but the process is basically, the chemical processes are the same. So Eastern Serbia has a long tradition of mining copper, and these various international companies have been engaged over the decades. And I have to say that this mining has been, to some extent, economically feasible, but also the environmental impact has been incredibly bad. This is the town of Bor. This is the major mining town in Eastern Serbia, where the mines have practically reached the town. There have been spillovers and leachings from the landfills and from polluting of the local rivers. I will not go into many details, but I will just say that the death rate or the mortality rate in this part of Serbia is 10% higher than the national average. So we can say that, yes, there is mining, but there's also an absolutely unacceptable way of trying to overcome the consequences of this mining. So therefore, you can understand why, if we go back to the map, that this finding of a lithium ore in the western part of Serbia caused a lot of concern whether the same type of damage will be instigated in the western part of Serbia. This is a lithium ore that, besides lithium, contains boron, which is also very attractive for modern technologies. And let's see, at what level can there be cooperation in terms of achieving, if not green mining, but at least a sustainable future? I bring your attention to the European Corporate Sustainability Due Diligence Directive, which was adopted at the European level last year, and now is in the process of being implemented at the national level. So it is binding, as was the previous case. There were some things that were mentioned that were not binding. But the interesting point is also that non-European Union countries, such as EA countries, are also obliged by this directive. So the question is, how will this affect other countries and, for example, countries that are candidate countries for the EU? Specifically, in terms of for Serbia, Serbia signed a memorandum of understanding with the EU on raw materials. And this partnership actually, on paper, sounds perfect. There will be very strong cooperation with developing the value chains, and there will be a very strong focus on standards, environmental, social, and governance. So as I said, on paper, it seems very promising. So remember, this is the summer of 2024. Now I have to introduce some other points, and then I will bring you back to July of 2024 a bit later. So this mining project is happening in the Jadar Valley, and you can see this is a traditional farming area with sort of looks a little bit like Tuscany, and it really is, very quaint when you go there. But the importance of the Jadar Valley is not exclusively its surface. Also, what lies below the Jadar Valley is extremely important. And these are the most relevant reserves of groundwater that Serbia has. And this is actually a national strategic resource. And one of the biggest ones, now I don't have a pointer, it would be that area here, which is actually where the Jadar Valley is. So any type of threat in terms of pollution could possibly threaten the water supply of half of Serbia in the future. So, this is not just a mining project that we're talking about. The consequences could be much more. So what is the Jadar Valley project? It's a project that would develop a complex that, besides the mine, would include a processing facility and also 2 landfills for the industrial waste. In order to set up this complex, 20,000 people need to be dislocated, which is affecting more than 20 villages. And not only that, a lot of wooded area has to be cleared. And this means that actually, in case of torrential rains, there could be additional flooding and then polluting of groundwaters. And I have to say that the local rivers in this area have been known to flood occasionally, which means they could reach these landfills where the industrial waste is located. So already with a very even simple analysis, we should see that there are very many risks that could be entailed in this project. As far as the company engaged, this is the Rio Tinto company. You have heard of it. And actually it's done by its local subsidiary, Rio Savo. The technology is newly protected by a patent, or it's dealing with a solid ore. And in terms of chemical engineering, it's nothing that spectacular, but there are very high quantities of aggressive compounds that are being used, which means it requires really tight security, that no leaching or somehow loss of these compounds is is happening. And also this process needs a lot of water for cooling. And it cannot be a completely closed process of circulating water. Local resources of water will be needed that actually surpass the capacity of the local rivers. And finally, one very interesting point is that the technology itself, in the end, as waste products in the water, did not meet the Serbian legal limits for boron. So what did the Serbian government do? They lifted the limits. There are now no limits for boron in water in Serbia. Now, you would say, who cares about boron? Boron is very useful for the growth of plant life in very small amounts. But if you exceed a certain value, it becomes deadly for plant life. So that means there could be long-term damage in terms of this boron-rich water to the soil. So there are many things, as I said, already at a glance that are threatening this project. So Rio Tinto has been present in Serbia for more than 20 years. It did a lot of exploratory drillings and came to the conclusion that it wanted to set up this mine. And since 2017, it has been closely cooperating with the Serbian government, signing various agreements in a very non-transparent way. And this is where the trouble really starts, because finally in 2020, the government signed some additional agreements with Rio Tinto and adopted a spatial plan that would allow for the implementation of this project. And that's actually when the citizens started to organize. And first we had local protests, and actually they swelled to the national level, where you had tens of thousands of people in the street. And finally, after about a year of protesting, the government finally receded and it revoked all of the permits and it stopped this spatial plan. And the citizens were satisfied. And somehow we thought that this issue was resolved. Unfortunately, after elections, the government reverted its decision and decided to continue with the project, that it had been a mistake to stop it. And despite protests and various petitions, the project went on, and also the Serbian government started actually the process of making this memorandum of understanding with the European Union. So I think you can understand the overtones of that this was a way to somehow protect this project regardless of the consequences. So we had a situation where protests about the project were still happening, but unfortunately, in May of 2023, there were two back-to-back mass shootings where 19 young people and children lost their lives, and this completely changed the dynamic of social events in Serbia, and some mass protests started focusing on against violence, against corruption, against the lack of rule of law, the fact that those who were committing these atrocities were not being processed properly. And these protests took months. They lasted for more than 6 months, unfortunately not leading to any concrete result. What happened in the meantime? During these protests, the government was not asleep. They were working very hard. And we have actually just before the signing of the Memorandum of Understanding with the European Union, the Constitutional Court of Serbia actually reversed the government decision, and that spatial plan allowing the project to be implemented was going. So that is the situation, and of course, this immediately prompted new protests, but of course, as things in Serbia are always dynamic, and as I said, we have weak rule of law and unfortunately a strong tendency toward corruption that is now causing significant problems. There was an incident on the 1st of November 2024 when a newly reconstructed canopy at a railway station in a northern town in Serbia collapsed, killing 16 people. And this was the trigger for new protests that became so massive that they led to the resignation of the prime minister. On March 15th, we had more than 300,000 people marching in the streets of Belgrade, and you have to understand that Serbia is a small country with about not more than 6 million inhabitants, so this was really big. A new government was form, but still continuing with the same type of politics. So these student-led protests, strongly supported by the citizens, continue. They continue to this day. It's a very, very hot atmosphere. And I have to say, last week we had a new, again, focused protests regarding the project in the Jadar Valley, where this is seen as that the project in the Jadar Valley, the collapse of this canopy, other major projects are all indications of abuse of power, lack of rule of law, weak captured institutions, call them what you want, that it's not even a question that we discuss the technology that will be implemented. It's a question of whether Serbia in the moment is in the state to implement proper monitoring and control of the processes that would be implemented in this technological complex. So we come back to the directive. The directive, when implemented, will also oblige companies, including Rio Tinto, and also companies that will be users of the products that will be made in this complex. And therefore, if these players, these actors are going against the directive, this project will be halted. So we will have several aspects. We will have aspects that a lot of money will be wasted for nothing. The whole process is unethical and against the interests of the population. So it actually shouldn't have started in the first place. But still, this is a reality, and that's why I think as a case point, it's useful to say, okay, I believe that in Western Europe or in the countries of the European Union, rule of law is something that is much more respected, but I think corruption exists everywhere. So to a certain extent, various incidents can be happening everywhere. Such directives are useful, but I also think this is also a question of supporting European values, where we need to stay on track that regardless of whether a country is a member of the European Union or not, the position of the European Union should be such that it upholds these values. So green transition, materials manufacturing, all of it ties in together. So of course we want profits, but I think not at any cost. So thank you for your understanding and for listening, and let's hope that until Serbia is ready to tackle in a responsible way such a project, that the project will not continue. Thank you very much.
Thank you very much. So I think we were right in the middle of technology, digital, and policy making, which I think concludes the talks with an interesting aspect. And clearly, we should not forget that even raw materials end up being used in digital technologies, and we end up having an environmental impact on those. So now I think it's the time to move to questions. Is there a question in the room, or should I start? Maybe I will start, maybe then. I will start probably to Rafael and Calina. There has been historically a lot of effort in the EU to recreate or to create a silicon business. There are a few companies. But as far as I can tell, I mean, even though there is regulation, even though there are legal aspects or there is money, it doesn't seem to take off. Am I wrong? And if I'm wrong, which I'd love to be, please tell us. And if I'm not wrong, what would be the killer thing that would help us? Rafael, maybe.
Now? Yes, it's just one. Yes, I don't know. The semiconductor business is a very strange business because there are in the old supply chain there are very few players. No, we know for high-end chips we know there are almost one player, that is the TSMC. That's very strange. No, maybe Samsung for memories, but for the people that does the machines that goes into that factories, this European company, the ASML, but maybe it's the wrong order. But in fact, this company have some key components from the US also, like the laser bit, I believe. Then it's a history of very unique players. Then this probably has something to do with the fact that Europe hasn't apart from this one, the lithography, hasn't been able to have the kind of one of these key players. No, everything started in the US. For political reasons, they moved. In fact, the one that founded TSMC was a person that was going to be the CEO of Texas Instruments at some point, and they decided maybe for social thing that was not the right person and went to Taiwan to build up this company. I think there is an opportunity for Europe to be a key player. It's a matter of putting all the effort and putting kind of coordination, more than coordination, because the talent is here. It's more than how we can coordinate the efforts to build something very relevant.
Okay. Calina, anything to add on this?
Yes, it makes sense. Although indeed the company ASML is market leader, and it's okay. It has some sites also in the US, but I think it's putting Europe in a very strategic position, and I hope it will hold it, including the ecosystem that is built in Europe. So
Okay.
yes.
Thank you. So there is a question, please.
Thank you very much, Alessandro Pacagnella, University of Padua. Let me add a comment about your question, which is fundamental about the curve that European semiconductor industries have followed. Yes, it is true that transistors were invented in 1947 in the United States, but let's remember that by year 2000, we had 3 European semiconductor companies among the first 10 companies in the world. ST Microelectronics, Italian, French, Infineon, German, and NXP or Philips, Dutch. So we were very strong by that time. Actually, during the 80s, there were strong political commitment, which passed through the first frame program, and then Jesse, and then Esprit, and then Eureka. A lot of efforts, a lot of money put by European community by the time, which were able to put our companies at very high rank. Then after the year 2000, there was a decline of attention, a decline, I would say, also of political attention, because we have not put so much effort as in case, for instance, of People's Republic of China. But in 2014, let's remember, they issued a very strong commitment about strengthening their integrated circuit industry locally. And they put tens, hundreds of billions of dollars that we missed to do. Basically, we woke up with the COVID when Thierry Breton in 2021 issued a very strong claim stating that we have, as European countries, we have to fight for our technological sovereignty. And this is what European Chips Act is trying to do, more or less successfully. At this point, I have a question for Rafael.
Okay, please.
Because, Rafael, we have seen something not very good running with competition between European countries. And there has been a fight between Germany to get Intel at TSMC, Poland with Intel, and they didn't work so well. France with Global Foundry in Grenoble, and okay, now it's passing. And do you think the same is happening also for RISC-V? Similar thing. I mean, there is no coordination. Do you think that there is a hope for a stronger supra national entity which may lead national interests towards a common interest.
Yeah, I think this is one of the things is missing. It's like a RISC-V agency, European agency that coordinates everything, because money at the European level, but it's money on the European countries. But there are a lot of projects that these projects seems sometimes that doesn't build into something like is creating a lot of talent, is creating a lot of engineers with training. But I think we need these kind of things that makes something that everyone envisions. No, that's a big European design. But it's hope, yes, it's hope that is happening. For example, in the supercomputers arena, at some point there are, I think, 5 supercomputers in Europe. They're like competing a little, not with the best. Now it's every year a new supercomputing is revealed, and there is no competition, because you know that in 5 years you will have another revision, and with the European country will put money. These kind of things need to happen. In RISC-V, we need an agency, and a central agency for RISC-V development.
Okay, thank you. Sir, please.
Just a comment with respect to the chips in the Silicon Valley. First of all, ASML operates on 2 key technologies. One is the optics from Zeiss, and the other ones are the lasers from Trump. Without those 2 technologies, ASML would not be able to do anything, and therefore we have a strong European hold on the ASML value chain. With respect to Silicon Valley and chip production, my comment is a few decades ago, there was a huge boost in the US, mainly driven by the defense systems. They put a lot of money in the chip industry in order to get, the resources, especially for the defense part. And given the new political circumstances and the new strategy also in Europe, this could also be something where the European chip industry could actually unite on that part.
Okay, thank you. Question? Yes.
I would maybe doubt that the defense side would be so integrated, because I think defense spending as a contribution to innovation or so is actually declining. I think the times of DARPA have been going back a bit, but my question would then be in the future, because we also mentioned Moore's law and like the doubling of the chips capacities every 1.5 years or something. From what I've understood so far, that law is, has been predicted already in the past to be ending, and maybe eventually it will end because of the just limitations. You cannot go below atomic scale, arguably, maybe you can, but to my understanding, that has been an issue, that you have come so close and to so small systems that it's just difficult to like continue getting smaller. And I'm not sure if this is correct, and if it is correct, how does this shape like the evolution in the future? Because now we may still see this coming back from the last 10 or 20 years as like a race, ever smaller, ever more computational power. But is there some kind of limit, and eventually we'll just converge to the limit, and then there's maybe no race anymore, because then there's just like one technological peak, so to speak? Is that trajectory a possibility, or is it going to slow down? Is it going to slow down at all? So yeah, could you comment on that, please?
So yeah, technical limitations of silicon at some point in time. Maybe Calina?
No, I think yes, the Moore law has predicted to finish at 4 nanometers or something, but still there are plans for 3, for 2, for 1. Then seems there's going to be a limit, but there are people is finding ways, I think, working with the materials, taking into account the quantum effects. No, what happens is the tunnel effect makes the transistor not to be a transistor, but the electron just move from source to drain. But by making different type of materials, I think you can do things. And yes, there is a limit, but for the moment, for the coming years, I think we will keep moving.
Yes.
Let me put a comment about the integration, the development of Moore's law that was claimed to die at 1 micrometer and then 215 nanometers and then 100 nanometers, and that's going down. Actually, we have stopped decreasing the size that we can draw the surface of silicon to about 15 nanometers because the wavelength of an extreme UV machine is 13.5 nanometers, so we cannot get down. Apart with the new machines, which only Intel is developing, which is the large numerical aperture machines. And in this case, we can go down to 8 nanometers probably. So we can shrink, but the play is not about shrinking, it's about putting more layers. And the evolution will be putting more layers. And when we go from planar technology to FinFET technology now to gate-all-around technologies, we're already opening the doors to get up. And please remember that the flash memories that we use in our cell phones have hundreds of active layers already fabricated, one over the others. So the possibility of increasing integration is not by squeezing, but it is by getting up and up. As you know, in Manhattan, if you want to put more people and more transistors on the same area, what do? You just keep adding floors to the skyscraper. And this is one possibility that has been already explored for flash, has been patented for DRAMs, which are the other big players, the memory, microprocessors. We'll see what happens with the gate-all-around technology, which already promises to have a single gate put on the footprint of a single transistor because it can just develop in a height.
Thank you. Any other question, Juan Antonio? Yes.
So I will have 3 questions, not one. Pretty general questions, some of them. So we have representatives from researchers and people connected to industry working on semiconductors. So I would have a question on what can be done from the high education institutions in order to contribute to the development of a sovereign or autonomous industry of semiconductors. We have been talking about companies and so on, but there is a need of trained engineers in disciplines that have, I'm exaggerating here, long disappeared from Europe in a long time. So that's my first point, an insight on that. Then to Professor Popović, you have been talking about the lithium mining project in Serbia. It's not the only project mining in Europe. So there are projects in Spain. It was published the list. There are projects in Czech Republic, in Germany. And I was thinking, seeing your presentation, I was thinking on this mention, this thought of a German minister considering the Jadar project, who said, well, the problem is not whether the Rio Tinto project will happen or not, it's whether it will happen with European partners or with Chinese partners. And that's kind of changing the side, right? So my question would be, what is the EU strategy that you would consider with respect not only to the Serbia mining project, but with respect to lithium exploitation in Europe and of course in Serbia as well? And last to Madame Jančiūtė, that's right. Sorry for that. You have been talking about the EU mostly landscape on the governance of post-quantum cryptography. Any insight on how is this being done or handled, for instance, in the US or in other regulatory environments, just in case you had any insight on that? Thanks.
Okay, so let's start with the development. Yes, please.
Or you can use this one.
So in Eindhoven University, we are actually adopting this other methodology, challenge-based learning. So in addition to dedicated courses or classical education, it's a hybrid way of integrating projects and students. So the vision of TUE is actually that we have like on-time learning. So while you are in parallel with developing projects, you are also actually following classic lecturing, where you immediately import your knowledge into such projects. So this is what we've been starting in the last years, and it's an ongoing process. But I think it's very important, and not only for the semicon industry, but also for healthcare and for other main, let's say, societal needs that we are, let's say, embracing. And yes, and maybe also just a small comment about the Moore's law. I totally agree. Let's say that it's very difficult to predict the future. And indeed, there are a lot of developments, not only from the technological part to approach the nowadays 8 nanometers accuracy with the large NA, but also we need to think of different paradigms also for computing, because we talk from the computational density point of view. So we basically in the same volume, which doesn't have to go subatomic, who knows? But we can, let's say, put more computational power. And indeed, who knows? I mean, physics doesn't stop with electromechanical, but or magnetic, but also other type of energies. So it's very difficult to foresee how we are going to evolve. But very good question.
Well, thank you. I think the most important aspect we're talking about is accountability, because what's clear from the beginning with this project that there was really no proper SWOT analysis or cost-benefit analysis that was done in a transparent way. So this immediately caused mistrust of the public. And I'm not saying the technology is not capable, but it also requires a very strong system of control and monitoring that can be trusted. And what I can say is that I know now in Serbia, this is not possible. What I think we should all ask ourselves, is it possible anywhere? Because if business interest is so big, will it overpower objectivity? Because I don't want to go back, and I'm not sure how it ended, but there was the whole scandal with Volkswagen and the emissions. So I think when we look at the interests of large capital, there can be things that might go wrong, and we need to be more vigilant. And of course, it helps if there are European directives that are mandatory and obligatory for all countries, member countries and partner countries. So I think it's a long road ahead. There are, the whole issue of lithium batteries, whether it will continue or there will be other materials replacing lithium, this remains to be seen. But Serbia, of course, is not the only country with lithium ore deposits. And there are countries in Europe that have much more lithium than Serbia does. But one has the feeling that maybe it's not quite a balanced approach, that everyone is going for the lithium in their own backyard. So I think it's very difficult to discuss this without entering politics. And I don't think this is the right venue for a political discussion. But I think when we talk about the green transition, where we also talk about energy portfolios, there are so many aspects to this, that we really have to look at the big picture. And of course, there are strategic needs that Europe has, but there are also national interests that need to be maintained regarding sort of the safety, security, health, and future of a population. So it's not at all trivial. And I think with actually emphasizing a knowledge-based society, this is where we are going in the right direction, to make sure that people with integrity and knowledge are the ones that we are counting on to provide the information to make, for the politicians to make proper decisions. Thank you.
Okay, so I have spoken briefly about the US at the beginning of my presentation. I can briefly recap that the US has mandated its federal agencies to migrate to PQC, to migrate their information systems to PQC by 2035, and it has encouraged the private sector to follow suit. I can also mention that in the United Kingdom, National Cybersecurity Centre has been quite active in publishing various resources and guidance and encouraging the transition. And just recently, in March this year, it published the timelines where it has urged to have a plan of transition by 2028 and to fully transition to PQC by 2035. It is also interesting to mention that while, as I said, like globally, the American National Institute for Standards and Technology has been setting encryption standards, including the standards for PQC. Not all the countries are following it, and countries such as China or Russia, for obvious reasons, they have been developing their own standards. So various activities are also going on in various other countries like Japan, Singapore, and I have also researched PQC in transition specifically in the financial sector, and a lot of interesting things are going on there as well, and some central banks, such as in Israel and Singapore, have also directed their operators in the financial sector to start transition. So if you're interested what's going on around the world, the GSM Association, the Global Association of GSM operators in telecoms is publishing a very good overview of all the government developments. I can send you the link if you want afterwards, yeah. So that would be a brief overview.
Okay, thank you very much. I think it's time to close the session. I'd like to thank the speakers once again.